Chapter 18, Blood, Screencast 2. This screencast will be focusing on erythrocytes or red blood cells. Quite often, I will think of red blood cells basically as a bag of hemoglobin. Keep in mind, we are not going to consider them as true cells because they are lacking a number of really critical organelles. They will not have mitochondria, and they also do not have nuclei. Now, they are small and they are flexible, and their overall shape is described as a biconcave disc. And kind of think about the candy Smarties, how they're thick on the edge and thin in the middle. That's what we refer to as a biconcave disc. And there will be some proteins that are actually going to be providing the overall support and flexibility that we know that is associated with red blood cell. Their primary job is the transport of oxygen and carbon dioxide between tissues and the lungs. Now, it really is all about hemoglobin, and hemoglobin is a red pigmented protein, and it is responsible for the transport of oxygen and CO2. We consider it to be oxygenated when it's loaded with oxygen, deoxygenated when some of that oxygen has been released. Each hemoglobin molecule is composed of 4 globins. That's a total of 2 alpha chains and 2 beta chains. Regardless, each of these chains has a heme group, and that is what oxygen actually binds to. So that is the iron that's necessary. So each hemoglobin molecule can actually bind 4 oxygen molecules. Now, one of the things to remember here is when we talk about the binding between oxygen and iron, it's going to be relatively weak. And this is important because we want it to be reversible. So in the lungs, hemoglobin will be able to pick up that oxygen, but when it gets to tissues, it'll be able to release that. When it comes to the transport of carbon dioxide, it is going to be bound to the globin protein, not the iron. That's important, okay? So oxygen will be binding to the iron or the heme component, whereas carbon dioxide is the globin portion of the protein. This also is going to be a relatively weak binding, so basically you can pick it up and let it go. Now here we basically look at the underlying structure of hemoglobin. We see the centrally located iron molecule, and that really is what's responsible for the oxygen transport. Here we can actually see the 4 separate proteins and chains that make up the hemoglobin molecule. Now here, we're basically looking how erythropoietin, or EPO, which is a hormone produced by the kidneys, will actually regulate the production of red blood cells. So the stimulus is going to be a decrease in the oxygen carrying capacity of our blood. The receptor is actually within the kidney, and that is what's going to detect the decreased blood oxygen. The kidneys now will actually produce and release this hormone known as EPO into the blood, and the target is actually going to be red bone marrow. And remember, this is where formed elements are produced, and EPO is actually going to increase the rate at which red blood cells are being produced. The overall impact is an increased number of red blood cells are going to enter the circulation, and now hopefully we'll be able to increase the transport of oxygen. And these increased oxygen levels will be picked up by the kidney. And now, this is a classic negative feedback mechanism. EPO will no longer be released as oxygen levels are back to homeostatic levels. Now, when we look at the concept of blood doping, there's different ways in which blood doping can be done. One is basically the self-donation of red blood cells. So blood is actually removed prior to competition. This is going to result in EPO production, and more red blood cells are going to be produced. Then those red blood cells are going to be transfused back into that subject prior to competition. Now, this isn't always how it's done, because what ended up happening, athletes were not using their own blood. They were actually using someone else's blood, and that actually resulted in some athletes actually picking up bloodborne diseases such as HIV and others, but primarily that one. The other type of blood doping is pharmaceutical EPO. And so remember, EPO is a hormone naturally produced within the kidneys, and its job is to increase red blood cell production. Now, there are a number of dangers that are associated with blood doping. One is an increase in blood viscosity. This actually makes the heart have to work a lot harder. Now, this can actually result in permanent cardiovascular damage, and some people have actually died from this procedure. And keep in mind that blood doping is actually banned from competition and sport. Now here, we're basically looking at the process in which old red blood cells are broken down. Now, there are two places where this is going to take place. It's going to take place within the liver and the spleen. And what's happening, old red blood cells are broken down into their three primary components. And that is going to be iron and the globin and ironless heme. So we're going to actually see that come into biliverdin or bilirubin, and bilirubin will be transported by albumin within the blood, and eventually bilirubin will be removed from the blood by the liver. Bile containing bilirubin will be excreted into the small intestine. Bilirubin will be converted to urobilinogen in the small intestine, and most of this is actually going to be converted in the large intestine and gotten rid of in the feces. Some will actually be reabsorbed into the blood and eventually excreted in the urine. So what the body does recycle will be primarily the heme group and the iron. That's really important. We don't want to let that go to waste because, a lot of people have problems with iron. But the key thing that we want to remember from this process is where is it actually taking place? And the two organs of the body that are primarily involved with what's happening to or degraded or red blood cells are going to be the liver and the spleen. That's the important thing that I want us to remember about this. Now, you may have heard of the clinical condition known as anemia, and anemia is basically a generic term used to describe a decrease in oxygen carrying capacity of the blood. Regardless of the underlying cause, the symptoms are going to be similar. Lethargy, shortness of breath, pallor, palpitations, and basically a decrease in endurance. Now, probably the most common type of anemia is iron deficiency. And remember how important iron is because that is the part of the hemoglobin molecule that's responsible for oxygen transport. We can have aplastic anemia. This is when the red marrow is defective, and that is generally due to poisons, toxins, or exposure to radiation. We can have a congenital hemolytic anemia. This is a genetic defect in which red blood cells are actually destroyed. We have erythroblastic anemia. This is when there are large numbers of immature cells, and this is due to an abnormal or accelerated maturation of cells. Hemorrhagic anemia. This is due to blood loss. We have pernicious anemia. This is actually failure to absorb vitamin B12 due to the lack of intrinsic factor. And then we have sickle cell disease. And this is a genetic defect in which the hemoglobin is abnormal and red blood cells have a totally different shape. They're no longer biconcave discs, and they're going to have a sickle shape, and hence the name of the disease. Now, some of these types of anemia can easily be treated by EPO, but not all of them. The next topic that we have to address that's associated with red blood cells is blood typing. And so there's two things that we have to keep in mind here. We're going to be introducing surface antigens. They are actually on the surface of the red blood cells. And then we have antibodies, which actually will be circulating in the plasma. So if we look at type A, what we see here is the surface antigen is the A antigen, but notice the antibody. We will find anti-B antibodies within the plasma. So the rule of thumb here is you will have the antibodies for the antigens not on the red blood cell. So let's take a look at type B. So now we have type B. That will have that particular surface antigen, yet circulating in the plasma will be the anti-A antibodies. If we look at type AB, we basically look at A and B antigen on the surface of the red blood cell, but notice there will not be any antibodies. And remember the rule. you will have the antibodies for the antigens not on the red blood cell. Since both A and B are on the red blood cell, we're not going to see any antibodies. The last type is type O, and this has no surface antigens at all. So it will have both anti-A and anti-B, but the thing to remember about type O, it is the universal donor. And it is the universal donor because it does not have any antigens, so there's no way that it can actually cause an immune response. Now, there is another antigen known as the Rh factor, now known as surface antigen D, and this is what determines if the blood type is positive or negative. Now, one thing to keep in mind here is generally you will not have antibodies to Rh. And the only way to get anti-Rh is to somehow being exposed to an Rh positive blood. So typically what we will see, ABO group and Rh are reported together. For example, if all three antigens are present, the blood type is designated as AB positive. Now, I have just the A antigen. I am negative for Rh, so my blood type is actually A negative. Now, what this particular slide is talking about who can donate and who can receive specific types of blood. This is not something that you are responsible for. One of the things that I want you to remember, though, is type O negative is the universal donor. So all people can basically receive type O negative as there are no antigens, so you don't have to worry about any antibodies at all. Now, if someone is going to receive the wrong blood type, what happens is going to be agglutination. And what agglutination is the antibodies in the recipient bind to the transfused erythrocytes and they clump together. And this can be a real problem because it's going to block blood vessels and actually prevent normal circulation from taking place. This also can cause what's known as hemolysis, and that is the rupture of red blood cells, resulting in significant organ damage. Now here we're basically looking at what's happening in someone that received the wrong blood type. So we basically have a type B recipient, but for some reason they're getting blood type A. And so what we're going to see now basically is that agglutination or clumping is taking place within the recipient of the wrong blood type. Now, what we're looking at here is the agglutination test, and this is how we actually type for blood. And so the thing to remember here is if you add a particular antibody, it is going to agglutinate if it is the antigen present on the red blood cell. So that's one thing to keep in mind here, okay, when we're looking at that. Now, probably a more important situation, and this is one of the few times where I actually will be holding you responsible for the concept of Rh. And the issue here is we have an Rh negative mother. Now, if we look at the first pregnancy, we're actually looking at the fetus as Rh positive. Now, at this time, within the mother, we have a Rh negative. There is no antigen D at this time, but there are not going to be any antibodies because as of now, there has been no exposure to that. Now, if we look at pregnancy number 2, now we actually have the problem. So now the mother is Rh negative, but she actually has anti-D antibodies. So this can be a significant issue, especially if we're talking about the developing fetus is going to be Rh positive. As noted, the first pregnancy is not an issue, but any pregnancy further down the line, because anti-D antibodies from the mother are there, they can actually attack the red blood cells of the fetus and create hemolytic disease in the newborn.